Let's design and 3D print a grinding wheel balancer. Of course, if one grinding wheel balancer is good, two's even better, right? Right?
Welcome back to Cloud 42. I'm James. Last week, I balanced a grinding wheel for my surface grinder using an RC propeller balancer, and it kind of worked. At least I think it worked. I'm still not getting the kind of surface finish I want from the grinder, but there are a whole bunch of variables involved, and balance is just one of them. But I've never been accused of not beating a dead horse, so let's see if we can make a better wheel balancer that's more sensitive than the Dubro toy I used last time. And while we're at it, let's 3D print it, just because we can, and also because it's a really easy way to prototype things quickly. Can always make one out of metal later if it works. Though, if it works.
This is the design that I came up with. Now, this concept is nothing new. We've got two pairs of bearings, and those bearings will support the balancing arbor, and then of course the arbor will have the wheel sitting on top of that. And the idea is that these bearings provide a low friction pivot for the arbor so that the heavy side of the wheel will sink. This actually works exactly the same way as the Dubro prop balancer that I used last time, except the Dubro prop balancer uses metal discs here and little tiny pins for the pivots. Now this is totally dependent on the friction inherent in the bearings. So if we use sealed bearings or greased bearings, there's a very good chance that the drag will be too great. I did some initial testing with some oiled bearings, and I have ordered some dry ceramic bearings that I think are going to have low enough friction to make this possible. But we'll find out soon whether that will actually work or whether all the people who told me this won't work were right. I'll roll the history marker here back to the beginning, and I started with a single sketch. And this is often how I start something like this, is with a single conceptual sketch that gives me kind of the dimensions that I'm working with. And in this case, I've drawn in the grinding wheel at the correct diameter. It's about 8 inches. I went ahead and called it 203 millimeters just so that we could deal with slightly oversized wheels and they would still clear. And those are pivoting on a 15 millimeter diameter shaft. Now for the supports, I've just drawn in the bearings. We're going to use 608 bearings. So they are 22 millimeters on the outside and have an 8 millimeter bore. And I've just drawn in a couple of overlapping circles here so we can see how close together those can be positioned. And then this will serve as our guide to model everything else. So the first thing I did is I went up here and said, insert McMaster car component, and I went and searched and found models for the bearings. Brought those in and attached them. And ultimately I just joined those up to the sketch itself so that I could have them in the right position. And I've just offset those. If we look at one of those joints, I've just offset it a 0.5 millimeter away, and one bearing is on each side so that we end up with 1 millimeter of clearance between the bearings. And this gives us the basic structure that we need to work around. Now we just need to model something to support the bearings. So I just created a new sketch here, and then this sketch has projected lines from the dimensions on the physical bearings so we can see where those are, where the inner race and the outer race are. And then I've got offsets from the outside for the amount of clearance I want around the bearings. And I've added some tangent circles on the side to give me an idea of where I want to place fastening screws for the assembly that's going to clamp these together. And then once I have that, I can just take extrusions using the profiles in this sketch and taking them from the surfaces of the bearings or to the surfaces of the bearings and actually construct the geometry around this. And this is what it looks like. So again, I've just used that sketch and pulled off all of this geometry. If I hide the bearings, you can see here a little bit better what's going on. And you can see that we've got recesses for the bearings. We've got some faces here that will register on the stationary inner race of the bearing and clearance for the bearing to rotate. And then I went ahead and modeled the pins to hold the bearings as well. And then to support the other side, I did exactly the same thing with the same sketch and just built up the structure over here on the other side of the bearings. And that gives us a cap that fits over them. So if I hide the original support, you can see we're providing structure to support the other end of the pins to support the inner races of the bearings. And when these are sandwiched together, it then traps the bearings in place so they can't move, and those pins are supported on both sides. Then we just need some holes. I got some counterbore holes here in this piece, and we've got some holes for threaded inserts in the other side. And go ahead and bring those threaded inserts in. I went ahead and just imported those, went and searched for those on McMaster-Carr as well. Now with the clamps done, we need some legs. So I just went ahead and created a sketch of the legs, extruded those, and added some fillets to make them look nice, and then created a mirror for the legs on the other side. Now technically this isn't a mirror, this is actually rotated. And I just did that by creating a sketch with a center line and using the circular pattern to pattern those components. Then we just need some pieces to connect those together. So I just did exactly the same thing, sketched and extruded and built these C-shaped pieces, add some fillets to give it some nice curves, and then do the same trick and put in holes to attach it together with screws and holes for threaded inserts. Then I went ahead and brought in the screw models from McMaster-Carr, put them in place, and that gives us a complete model that should be ready to build. One little trick that's really handy in Fusion 360 is if I open up these components, like if I open up this bearing support side piece here and drill all the way down to the body, you can click on the body and give it a name. So I gave that a name, bearing support. So now when I come in here and say 3D print and I select that body and I don't want to send it to a 3D print utility, I want to save it to a file, click OK, it will pre-populate the name of that body into the name of the STL file. And this is really handy, especially if you're going to export several times as you're iterating, because they'll always have the same name, and then it will prompt you and ask if you want to overwrite the same file, which you probably do. I printed all the parts in Bamboo Lab high temperature nylon with carbon fiber, and they just turned out great. This stuff is really tough. I've been playing with a lot of filaments, and this stuff is pretty remarkable. And then just put in the heat set inserts using a soldering iron. And this was a really slow process because I really didn't have the temperature set high enough. What you're watching here is 10 times normal speed. They just sunk in very, very slowly. I didn't want to run the temperature up too high and push it too hard because I really didn't want to melt and have to reprint the parts. But, you know, I just took my time and set the temperature a little bit above the extrusion temperature that I use with the material, which is like 290 Celsius. And they went in and they held securely, and here are the results. I really do like the look of the carbon fiber nylon parts. These are a little blacker than the cheaty carbon fiber I've used previously, and the fit right off the printer is just fantastic. I started out with a bunch of allowance for fit, but ended up dialing it back down to 0 because the parts were coming off pretty much exactly on size. You can see I added some little tabs here to make assembly easier, just so the parts will line up on their own, and screws all lined up and went right in. It's almost like planning things out in CAD actually works. This is the first time I've used tabs for alignment in assembly, and I will do that again. That made this job really easy. Now for bearings, I wasn't sure exactly which ones would work the best, so I ordered a few different styles of ceramic bearings. I'm just going to pick one based on how they look, and we'll give it a try, and if they are insufficient, we'll try some of the others. Now, these are ceramic races with ceramic balls and PTFE Teflon cages around them, and they look really good. Fortunately, the laser etched writing is on the sides and not on the rolling surface, so that should make things a little bit smoother. Let's see how they fit. These should be 8mm posts, and they fit beautifully. I did some test parts with these smaller, and they just rattled around, and it turned out dimensioning them pretty much exactly on size worked better than anything else I tried. Snap the cap over that, put in a couple of screws to retain the bearings. Then we'll just do exactly the same thing on the other side. That is really satisfying when parts go together that well. Now let's roll something on it and see how they roll. And that's pretty smooth. There's not a lot of friction there. I did some testing with some oiled bearings, and these are quite a bit freer than those. I think this might actually work. I like the look of this too. Those white bearings against the black carbon fiber nylon. That is just beautiful. Let's get a wheel and see if we can actually balance it. I have a wheel here we can test with, and I have my balancing arbor. This is the arbor that I used in the last video. And if you remember, it doesn't really stick very well in the taper. I'm not sure how well these are supposed to be retained, but this arbor has no means for retaining it in the wheel adapter except the friction fit of the taper. So I went ahead and ordered the Tormach shaft. It has threads and a nut that are designed to hold the adapter on the arbor while balancing. So, I mean, I'm a little dubious on the quality of this thing, but it does indeed have a retaining nut. The shaft has what I would call some character. They literally threw this in the bottom of a cardboard box and shipped it to me. I ran a flat ground stone over it to try to clean it up, and it's okay, but it's not great. The real problem, though, is that the threads are not long enough for this style of wheel adapter. Apparently the Tormach adapters that came with the PSG 612 grinder were shorter. So there's really no way I can get this nut on here. In order to use it, I'm going to have to make a nut, something that will fit back down inside of that recess. And that's certainly something we can do. There's plenty of room for a nut in there, but it is kind of frustrating to not be able to use this as is. Let's take some measurements and see what we need. That looks like a 16 millimeter thread and 1.5 millimeter pitch. I'll get some dimensions off of the wheel adapter and let's go in the computer and design a nut, I guess. This is really a simple part and an easy modeling job in Fusion 360. I just started with a sketch with a couple of circles, extruded that to make a tube, and then drew another sketch on top to define the knob. Just used a circular pattern for some circles to make grooves for my fingers, and then extruded that, and that gives us the basic structure of the nut. We can create a thread with the Create Thread tool that is just up here on the Create menu, Create Thread, and you can define it, in this case, isometric thread profile, 16 millimeter M16 by 1.5. And then I just made sure that the modeled checkbox is checked, and that created a physical thread in the model. Instead of making this out of metal on the lathe, I decided to just go ahead and 3D print it in polycarbonate. Figured that would be much easier, and it should be plenty strong for this application. Let's try this again now that we actually have a locking nut. Put the shaft in, give it a little twist to seat the taper, and secure it with the nut. Now this nut is the second one that I printed. The first one was a little bit tight and I used the inside hole compensation in the slicer to get the thread fit exactly the way I wanted. And this is actually really nice now. Now this wheel was previously balanced here on the Dubro prop balancer. Let's see if it's still balanced. If I put the arrow pointing up, it stays put. If I point it off to the right, it pretty much stays put. So this is balanced as far as that Dubro is sensitive enough to detect. But if I put it here on the new balancer with the ceramic bearings, you can see that there is a significant imbalance there that the new balancer is sensitive enough to detect, but the Dubro prop balancer was not. You can see it's rocking back and forth, finding the heavy point of the wheel. There is definitely an imbalance here in the wheel that the Dubro prop balancer was unable to detect. Several people suggested in the comments that perhaps the weight of the wheel was too much and it was causing the Dubro to flex, and that was causing increased friction, and I think that's exactly what was happening. But this new balancer with the ceramic bearings is much more sensitive. But that sort of begs the question, if the ceramic bearings are more sensitive than the prop balancer, what about the rail style balancers that everybody told me would work better than the bearings? Is that going to be even more sensitive? I can think of one way to find out. The rail type balancer is even easier to model, and this is just a couple of round steel rails that the arbor rolls on and a structure to support them with some provisions for leveling screws. To model this, I just started again with a sketch showing where the wheel's going to be and the arbor, and then another sketch giving the cross section of where the rails are going to be, and then some structures around that for V-grooves to set them in and a V-groove clamp to hold them down. So I'll just go ahead and extrude that circle out to make the rail, then use a mirror to create a second rail in the correct position. and then just start extruding from the sketch to create the structure to support these. So I've just taken this out one side. We'll work on one side at a time and then mirror it. So I've got the basic V groove there. Then I've got a cap that will sit over the top of the rail to hold it down. Some more structure on that, and holes for screws to hold it in, and again, threaded inserts to hold that down. And I went ahead and put a little V tab on the end there to keep everything aligned. And then we'll just use the mirror tool to create the other side of that and start working on the structure underneath it. Just draw a sketch in here of generally what I want this to look like and start extruding. So there's a support to go underneath it. Put some chamfers on this and some fillets to make it nice and smooth and easy to print. We'll mirror that over to the other side and extrude a base across. So now we have a one-piece support that will support the two rails. And then we'll just go ahead and copy those caps around all the sides, put some nice fillets on to make it nice and smooth and strong, and put in tabs with holes for the leveling screws. And those are sized to accept threaded inserts for M4 screws. So this should be ready to send to the printer. Now this model actually does use a fair amount of material. I printed it with a bunch of perimeters to make it nice and strong because I really didn't want it to be flexible. I did print this in PETG just because I was running out of the carbon fiber nylon material, and the PETG should stay nice and flat and it should be plenty strong for this application. The rods themselves are made out of W1 tool steel. This is just 3/8 inch W1 drill rod, and we'll start by facing it off. I am running this pretty slow because there's a big long piece of rod sticking out the other end of the lathe headstock. Put a little chamfer on the end of that and then pull it out and part it off to length. This is sized for 150 millimeter rods, and I'll just use a parting tool to part it off. I'm using a carbide parting tool here that I've honed to a very sharp edge, and it cuts through this W1 beautifully till we get to the center, and then we'll just snap it off, flip it around, and face off the other end. Take off the little nub, take a little cleanup cut. I don't care too much about the length. I was pretty close with the parting blade. Then we'll just round over the edge with a file to make it easy to handle. And that is it. Make another one of these and we should be ready to assemble this thing. The plate was actually a little bit challenging to get out of the printer with one hand because it has the big flat part adhered to it, so it has to come off of the magnet all at once. But it did come off and the part did stick to the bed, which is kind of the whole point. This one was printed with a brim. You can see the brim tears off pretty easily, so we'll get that off and get the heat set inserts in. Because this is PETG and not the carbon fiber nylon, the melting temperature is quite a bit lower, and so it's quite a bit easier to get the heat set inserts in, especially since there is no fiber content. So I got all 5, 6, 7 of those in. Those set in nice and neat and flush. We should be ready to assemble this thing now. Start by setting the rods into the V grooves, and those turned out nice and flat. I'm really happy with how those seat in there. And then we'll just put the caps on the ends and secure those with some M4 screws. I'm using M4x16 screws. This is just about my favorite size for putting together 3D printed parts. Everything you've seen me do today is with M4x16 millimeter screws. And those seated in beautifully. The clamps are holding them securely. I'm very happy with how that turned out. The edges are flush. The screws pulled everything down nice and centered. Now we'll go ahead and put in some screws for the leveling. Technically, we only need one of these, but since the bottom was flat and I wanted to be able to tilt it either direction, I used 3 screws. You can see it's definitely not level sitting here on the bench, but we can adjust that. Turn the screw this way, it goes to the left. Turn the screw this way, it rolls to the right. And I'll find a happy medium where it balances. To compare the sensitivity of these, let's find the high spot here on the bearing balancer. We'll just let the heavy side fall, let that settle out, and then mark on the blotter here where the light point is, the point that's sticking straight up. And now that we've got that located, we can move the wheel over to the rail balancer and perform the same test and see where it settles. We'll set that so that it's 90 degrees off from the settling point. And of course it rolls Motion seems relatively similar. We'll just let this settle back and forth until it finds its final position. I'll kind of touch it here to damp out the end. And it looks like it ended up in about the same place. Let's try actually balancing the wheel. We'll use the bearing balancer to do that. This way we can get it a lot closer and test the sensitivity a little bit better. I'll turn it around so the weights are pointing this direction, and we'll do the same thing. Find the point where the light side is up, and then I will loosen the screws and move the weights slightly toward the light side of the wheel. And then we'll see how it moves with that new weight distribution. It's closer, but there's clearly still one side that's heavy. It is about 90 degrees out from where it was. So we'll get that located. Let the wheel settle and find the high spot. We'll try this from several different positions. Then we'll make another minor adjustment to the weights. It's getting really close, so it's not going to take much. And after 2 or 3 cycles of this, we eventually get to the point where pretty much no matter where we put the wheel, if it starts out stationary, it stays in that position. I think that is just about as balanced as the wheel is going to get on the bearing balancer. We've reached the limit of the sensitivity. Now, the interesting question here is the wheel actually balanced? And of course, the answer is no. There's no such thing as perfectly balanced. But let's go ahead and give this a try on the rail balancer. We'll just confirm that it is still level, and it is. And then let's see if the rail balancer can detect any imbalance in this wheel that we were unable to find with the bearings. Looks good in that position. Looks good there. We're seeing imperfections in the finish on that arbor. That looked pretty close. Let's try a little bit further in that direction. Boy, that looks pretty good. But there is one position I can put the wheel in where it does roll away. So there is a tiny imbalance here. It's very, very small. Let me go ahead and make a tiny adjustment here. That was not much. So it looks like the rail balancer is slightly more sensitive, but is it enough to matter? It was a pretty small adjustment, so I guess it depends on how close you want to get. Let's try this with the actual wheel that we're going to grind with, and we'll do the same thing. Check it on the bearing balancer, and of course this one was previously balanced with the Dubro, and it looks okay in that position, but in some other positions there's definitely a remaining imbalance here, so we'll go through the same dance here, move the weights around, and get it as close as we can on the bearing balancer. And it took about the same amount of motion as it did with the white wheel, so we're getting consistent results. And that looks pretty good. I think that's about as close as we're going to get it with the bearings. It kind of, no matter where I put this, I'm not seeing any kind of motion. So if that were the only balancer I had, we would call that good enough. Let's check it with the rails. And as it turns out, that was close enough. I can't detect any imbalance here with the rail balancer that I was unable to find with the bearings. So what does this lead us to as far as a conclusion? Well, we know because of the experience with the white wheel that the rail balancer is more sensitive than the bearings, but they're also really close. And the bearing balancer is easier to use because you don't have to level it, and because it doesn't shift around or skid or risk falling off while you're messing around with the balancing screws. So your choice, but I think the bearings are probably good enough. Let's try it on the grinder. Go ahead and mount the wheel back on the grinder, put the nut on, and tighten that down. Got a whole bunch of comments in the last video for using the Knipex plier wrenches for tightening that down. Lots of people telling me it was a horrible thing. One person who was even self-conscious enough to realize they were going to be told that they were Knipex pliers wrenches. But if you have a problem with it, feel free to put down in the comments exactly what the bad thing is you expect to see happen if I continue using those. With the spindle running, I can put my hand on it here, and honestly, I don't feel anything. After balancing the wheel on the Dubro prop balancer last time, I was actually feeling a little bit of vibration. It was quite a bit lighter than I was used to, but now I don't feel anything at all. This thing, I can't even tell that the spindle is running. So the balance is definitely better than it was. One thing you may notice here on the grinder is that I now have a vacuum attachment. I went ahead and 3D printed a flexible coupler here so that I could attach my shop vac directly to the dust collection port. This is the first time I've tried using TPU to print vacuum adapters, and it worked great. I will definitely do that again. Start out by dressing the wheel since we've had it off the grinder. This probably is not strictly necessary since it's still on the adapter, but we want to give ourselves every chance of getting a good grind. Start by grinding the same soft steel vise jaw that we ground last time. This is 1018 mild steel. I've just touched off, and I will go ahead and make a pass across here just to make sure everything is level and I know exactly what height I've got the wheel at. Then I'll lower it about 1 thou, maybe 1.5 thou, and just make another pass across. You can see the sparks are getting caught by the vacuum and pulled up. There are only a few that are escaping and ending up in the rag on the shield down on the end of the table. That's really working great. I wasn't sure how well that was going to work. I was worried that I was going to need to create something much more elaborate for dust collection on this machine, but the stock guard's working well. So after taking a pass across, I'm now taking another pass, just taking about 1/10 just to clean up the surface. And with that complete, I'm taking a spring pass across just to spark it out. I'm not really seeing much. The coolant could be suppressing what sparks are there, but that gave us a pretty good grind. Now in addition, I'm also going to grind something hard. These are bearing rollers from a large roller bearing. These were provided by a friend for a 5-block test. He asked not to be identified because he doesn't have any more to give away. I really appreciate it. Thank you very much. You know who you are. I just love the way these grind with the pulses of bright sparks coming off of them. They grind very differently from the soft material, and this will give us a good comparison to see what kind of surface finish we're getting on hard stuff. Let's take these over to the bench and see what we've got. If you don't remember, this is the finish we were getting last time. You can see that kind of fish scale pattern in the grind that was, I think, caused by the wheel imbalance. And here is the grind we got today. And boy, that is just a night and day difference. That fish scale pattern is pretty much gone. If you look really close, I think I can see the effect of the corner of the wheel. Stan Zinkowski left a comment last time letting me know that if I knock the corners of the wheel off with a Norbide stick, it'll help with that, and I will try that. But boy, what we're getting on this today is so much better than what I was getting a week ago. Let's take a look at the hard bearings, and the story continues. These are just beautiful. I would be happy with that grind on just about anything. I've been told that hard materials grind a lot better than soft stuff, and boy, does that appear to be true. I stared at these for a long time trying to find any imperfections that I could nitpick. I saw some things that looked like maybe kind of shadows of the edges from the interrupted cut, but ultimately I think that was just skin oil or fingerprints that got on there when I was cleaning them. And if I wipe that off, the finish looks fantastic. So I think we've got the wheel balancing problem licked. I do have both of those balancers. I'll play with them. I like the bearing one because it's easier to use, but I'll keep them both around and we'll see how things go. But for now, I think the wheel balancing problem is licked.
That was fun. One of the big benefits of using a 3D printer for prototyping is that it can make the parts while you do something else. Though this ceases to be a benefit if you sit there like a puppy the whole time watching your parts materialize. Not that I would ever do that. As always, the 3D printable files for both balancers will be on Patreon. Patrons can download files for all of my projects and get a little peek behind the scenes. If you're already a patron, thank you. You are a part of what I do here and you help make it possible. Thank you for watching.